Hi, welcome to Lecture 8 of Quantum Physics for Non-Physicists, and this is a re-recording, which means that I'm going over Lecture 8 again. If you watch it live, it should be covering the same material, it's just a bit neater, more neatly organized. Good. So this is a Thursday lecture, which means it's only 45 minutes. Good, so today we will just finish what we started last time with a Gaussian wave packet. We'll just see how it evolves as a free particle. And then we'll talk about the dynamics of non-interacting systems. So this means when you have several subsystems, but the Hamiltonian doesn't contain any interactions between them. And one example that we'll see is the free evolution of a particle in 2D or in 3D in space. Okay. But I'll give you some general rules before I go to an example, and the example will be again the Stern-Gerlach experiment, which if you remember, it's a way of measuring the spin of a particle by measuring the position. So somehow we couple the spin of the particle to its momentum so that the particle goes up more or less if the spin is up and goes down if the spin is down. So then we measure at the end whether the particle is up here or down there to know what the spin was. So we will not see the full experiment yet because we don't have all the tools to analyze it, but we'll see part of it. Okay, and we'll get a bit closer to what's actually happening. Good. Our daily analogy is about the timing of questions. So, for example, if you want someone to marry you, you need to time more or less this question, right? You don't want to ask this in the beginning of the relationship when they're more likely to say no. But if you wait a little while and you see how the evolution is going and it's going well, then there is a time where it would make sense to ask and know that you get a positive answer with high probability. It could also be that if you wait too long, then you kind of lose your window of opportunity, and then the evolution of the relationship is such that then they're more likely to say no again. Okay, so in quantum physics, you can think, for example, as something we looked at some point, which was a spin that is rotating along the x-axis, okay, with time. So it starts here in the position 0, and then it rotates down. And so the probability, if you measure it in the 0-1 basis, in the z basis, the probability of getting the outcome 1 is of course given by this inner product, which changes with time. So if you wait such that it has revolved around 2 pi, that it is like the perfect time to ask if that's the answer you want. So then you get result 1 with high probability. If you wait for too long, then it will come back up, right? It will keep rotating, then the probability of getting 1 again is lower. Good. This to say that time evolution and measurements in general do not commute. It does matter which one you do first. Very good. So let us start. So let's recap a bit what we did last time. And this was just the end of the last lecture, which was Gaussian wave functions. Let me just copy this here. So we saw this was an example of a function in 1D. And in this case, it's given by a well-behaved function that looks more or less like this, such that the square of this function is a Gaussian distribution, a normal distribution, which in general behaves nicely. And then there's this term here, which tells us what the momentum of this particle is, right? Because we saw that sigma corresponds to this variance here. So sigma square is the variance square over x. The variance over p is given by the inverse of sigma times some constant. The average position is given by this x0 there. And the average momentum is given by this k, multiplied again by a constant, which, as per usual, is a Planck constant. Okay, so what we didn't see was what happens to this under free evolution. And let me just, before we go there, let me just do the same plot. So this plot was x, and we saw how it looks. And if instead I put p down here, and this is the wave function over p, which you computed in the tutorials, then you get again a peak around p0, and you get again a Gaussian, so this should be a symmetric function. Never mind my drawings, where this thing here is, that should be a square there, it's h by a square over 4 sigma square. Okay, let me just change the notes from yesterday's lecture so it's there. This will be h by square. Good. So this is, now suppose that this is the initial wave function, and now we want to know what happens under free evolution, right? So and this just meant that the Hamiltonian was given by p squared. This is the operator. I can put the hat there, just so we remember, over 2 times the mass of the particle. So what is now x, the average position at a point t, again. So what we found out last time in general for a general wave function is that this is x times 0 plus p at time 0 t over mu, right? But that is, in this case, it's just x0 plus hk over mu t. And what about p at a time t? Well, we saw that in this case it doesn't change, so it's just p0. So it's just h bar k. What about the variance over momentum? We saw that this is a time t, also doesn't change, so that's just square for sigma square. Well, what about the delta x square? There we saw that it was delta p square over the mass square, and this evolves quadratically. Then there was some beta t plus delta x times 0 square. And now we'll get into beta in a second, but I'll just tell you for now that this beta will turn out to be 0 for this kind of function. And so this is going to be just h square over 4 sigma square u square t square plus the original thing. So let me now tidy things here a little bit more. This is this. Sorry, we'll get there. You can go through great lengths to create space in a device that has infinite space. Okay, there we go. Now this beta, what it was beta was 1 over mu of 2x p at time 0 plus xp plus px at time 0. Now, it's not a particularly insightful calculation, so you can do it if you want, or we can put it in an exercise for you. But you can do the math and find out that for this particular type of initial wave, right, these quantities cancel each other. So this is going to be 0. Okay. This is not true in general, just for Gaussians. So what happens? So let's now draw the wave function at some later time t. So over p, not much happens. So it has roughly the same idea, time t. But over x, it does change a lot. So first, the average becomes here some x0 plus hk over mu t. Right, so let's put here. And then it also becomes much more spread, because we saw that this was the original spread variance, and it gets all of this new, so it becomes more spread. So maybe something like this, okay, where this is now the new sigma prime. Okay, so, and one interesting thing is that the narrower the wave function was at the beginning in position basis, so the smaller this initial sigma is, then the quicker it will spread out, because notice that the spread out has the sigma here in denominator, and it's multiplied by time square, so it will very quickly spread out. Okay, good. So this was the Gaussian in 1D, and now we're going to move to something else, and then we'll come back to it. Okay, it will be very useful in a bit. So let's first think about how we can have dynamics of composed systems. And what do I mean by this? Let me first give you an example before going to the general case. So an example would be an electron that is moving in space. Okay. Doesn't need to be an electron, it could be anything else, but let's just say an electron. And we can have the electron move in 3D space, but because then I'll just have to write one more coordinate everywhere, so let's just have it in 2D. And 3D is essentially the same. Okay. So what does this mean? What's the global Hilbert space? So the global Hilbert space, well, it's going to be some internal degree of freedom of the electron, which we'll see in a bit. And then, well, we have two space coordinates, x and y, like we saw before. Whereas here we have internal degree of freedom is going to be, in this case, the spin. If it was a photon, you could think of something called the polarization of a photon, which we'll get into later. But what matters here is that this spin is just a qubit, okay? Which means that Hs is the span of 0 and 1, and we'll write the subscript so we know which system we're talking about. Okay. And then we have what are called sometimes external degree of freedom, or orbit degree of freedom, orbital degrees of freedom. Okay, and this is the ones in the direction x and direction y. So we have, and the idea here is that they are continuous in this case, right? We could also have just 2 qubits or 3 qubits, but let's look at a more interesting case. Span of X, and now this is a big X, just to indicate which space it is, and small x belongs to R. And then you have Y, this is the span of Y, and little y also belongs to R. Okay? And we will look into this specific example when we talk about the Stern-Gerlach experiment later, which has exactly this, these 3 subsystems of interest. Okay, so this is an example of a composed system, and we want to know in general how we can go about looking at the dynamics of this or evaluating quantities. So we keep this example in mind for later, but now let's do the general case. And we'll do a general case with just 2 subsystems, and then it's very easy to generalize to more. So we just have HA tensor HB. Okay, system A and system B. And now these 2 systems could be interacting or not. And what determines whether they interact or not is the Hamiltonian. Okay, so what is a non-interacting systems? This is when H can be written as 2 parts. One that only acts on A, so some HA tensor the identity on B, plus something that only acts on B. And an example is the free particle, where we have p squared, but p squared we know that is just px squared tensor identity everywhere else, plus py squared tensor identity everywhere else, plus pz squared identity everywhere else. Okay, so let's see what happens to non-interacting systems in general today, and later on we'll talk about interacting systems. So in this case, so this is what we do today. So first, let's look at the evolution operator. The unitary operator. Okay, so what we know, we want to compute this u of t, which is e2 minus I h bar t. Okay. And that is, we just write it up, minus I t over h bar. And now what we have here, again, it is HA tensor identity on B plus identity on A tensor HB. Okay. So now this is still kind of a big exponential, and we want to simplify it. And to simplify it, we simply use a trick, which is that when operators act on different systems and they act locally on different systems, then they commute in general. So we'll just prove this, and then it will be useful also later for other things. So if you have MA, some operator, MA is any operator on A, identity on B, in the commutator of this with some operator that only acts on B. Okay. Then this is 0 because on the, let's write what this would be. So this would be an A, identity on B, identity on A, tensor NB, minus first the NB, and then the MA. Okay, but now because of the way the tensor product works, we know that they multiply like this, so MA will multiply there, and the identity will multiply there. So then what we get is MA, identity on A, tensor, identity on B and B, minus and now identity on A, MA, tensor, and B, identity on B, right? And now anything multiplied by the identities itself, so then you just get MA tensor and B minus precisely MA tensor and B. Okay, that's 0. And this is true in general, so we can keep this notion that operators acting on different systems commute. And what we also saw was that if the operators in the exponential commute, we saw this already, if I have two operators in an exponential that commute, then the exponential of m plus n is the product of the exponentials. Okay, and you can even change the order, it doesn't matter. Okay, so we just take these two facts and apply them to this unitary. So now we have that u of t is the exponential of minus I t over h bar, and here is the first one, HA tensor identity on B, and now the second one, minus I t over h bar, identity on A, tensor sum HB. Okay, but we want to do even better, so now I want to be able to write this in a simpler form. So let's take that, okay, and see, just expand this in the Taylor series, which is what we always do when we're not sure how to simplify some exponential. We just do it properly. So this is minus I t over h bar. What is it? Well, it's the identity, which is an identity on the two systems, minus the first power plus the second power, it squared, and now h8 plus the third power, and so on. Okay, we just did the power series expansion. Okay, so then let's see. Let's try to compute an arbitrary power of this, of an operator of this form that acts only locally. Okay. So in general, exponentiation of local operators. Then we have, so we want to know something like MA, identity in B, and we want to do this to some power K. Okay, so let's just write it up. MA, identity in B, MA, B. I'm just going to write K times. And so on. And now again, the same thing, right? How does this act? We know we act like so with the tensor product. We multiply locally, so we get MA square. And then here we get identity times identity, which is just the identity over B, right? And then all the other terms. Okay, and so on. So overall, we just have MA to the K times identity over B. So this is again fact to keep in general. So I put it in this blue box. Good. So now we go back to our exponent. So what does this give us? Well, it means that all these powers, they will end up having, so all of these powers here, when you resolve this exponentiation, it will end up with always the identity over system B, right? Which means we can put everything that's happening on system A on one side and then just say tensor identity on B. And what's happening on A? Well, it's A minus AT over H bar HA plus AT over square HA square plus the cube term and so on and so on. Okay, so but this is again just the power series of the exponential. So we have just e to minus it over h bar ha tensor the identity on B. Okay, which means what? Well, this is just the unitary evolution. If we only had evolution over A times the identity on B. Which means now, if you want to write the global unitary again, T, well, as we saw before, so this is just going to be E minus IT over H bar HA, the whole thing multiplied by the identity, tensor the identity over B, and then we have the other term, E, so it's this term up here that acts only on HB, so we have the identity over A. So identity over A, tensor E minus IT HB over H squared. Okay. And now, now we can multiply these two terms, right? It's a tensor product, so we just get E minus IT HA bar tensor product with E T HB. Okay. So this is our global evolution. It's really a tensor product of the two local evolutions. Where local, remember that this A and B could just be like the x coordinate and the y coordinate, for example. Good. So now we want to see also not just the global unitary, but we want to know how some observables evolve, right? In global observables, it's going to be a bit more complicated, but we'll look only at local observables. Okay, so now suppose that we have some observable M that is just MA times identity on B. And what could be an example? So if we had x and y as two different coordinates, you could have this kind of observable, for example. We could also have this observable that measures only, I don't know, the momentum on y and nothing on x, right? So we want to know how the x coordinate changes, or how the momentum over x or the momentum over y changes. Okay? So we're looking just at the evolution of these ones because they're easier. Okay. So we have delta t ddt. So how does it change with time? Usual thing. Average of the commutator with a Hamiltonian. Well, but now what's this commutator with a Hamiltonian? On the one hand, we have this MA identity on B, and on the other, we have this Hamiltonian that were two parts. Right? It was a sum of two terms, one that acts only on A and one that acts only on B. Okay. So we can split this into two. HA on B plus the commutator with the second term. MA identity on B and HB. Okay, where the second one, like we saw before, these are two operators that act on two different systems, so this is going to be 0. Right, they will commute. Okay, so we have here MA identity on B, HA identity on B minus HA identity on B, MA identity on B. Again, how do these things act? We have MA HA identity on B minus HA MA tensor identity on B, and just to be completely clear, these are the brackets. But now we can factor out the term on B, right? So this is just MA HA minus HA MA tensor the identity on B, which is just a commutator tensor the identity on B. Okay, so let's plug this in over there. In fact, let me just change the color of all this to be consistent. Color green, very nice. Okay, so ddt of m of t equals -1 over AH bar. And one nice thing already is that we only need to care with the commutator with the part of the Hamiltonian that actually acts on this system. And again, I remind you, this is only for non-interacting evolution. But we have something hidden here. So this is an average at time t, which means that we have here the evolved state. So now let's make this a bit more explicit to see if we can simplify this thing, or at least gain some insight into this. Okay, so what is this thing? MA HA identity on B. So as we saw, this is short for having here the wave function, the state at time t. And now here we have this thing. And now the state at time t. But we can write this state at time t more explicitly, right? So you can write it as phi of 0, u of t, then that thing here, that's just this, and here dagger because it's the complex conjugate, transpose conjugate. There we go. In this u of t, we saw before that this is just ua of t tensor ub of t. So we plug this in here. So let's just write this phi 0 like this. And now we have ua dagger of t times ub dagger of t. Now comes this thing. So MA HA, and now again UA dagger of T, UB. Oh, sorry, and now there's no dagger. UA of T, UB of T. Phi 0. Okay. But now we can just apply the multiplication directly, right? So this will apply here, and that will apply there, and so on. So what we get? So here's our initial state, and then we're going to get UA dagger of T, the commutation, and then I'm doing also the term on the right, UA of T. This whole thing. On system B, what's happening? We have UB dagger of T, then we have the identity over B, and then we have UB of T. Right? And there goes Phi 0 again. But now, what is this term here? What is this? Well, U is unitary, so we know that U dagger U is the identity. That's the whole definition of being a unitary evolution, right? And this identity over B in the middle is not doing anything. So overall here we only have the identity. Okay. So we have Phi 0, and now we have UA dagger of T, MA, HA, UA of T, this whole thing, tensor the identity on system B. Okay. And this is very insightful because now you see we don't have the evolution over system B at all anywhere. Okay, which tells us what? That only the local evolution on A matters. To know anything about a local observable that acts only on A. Okay? Which means that we cannot distinguish. If I give now this system A to Alice and system B to Bob, and I let Bob evolve his system however he wants, like whatever Hamiltonian he wants, then Alice cannot find out through observations only on system A what happened on system B, right? Because the average of any observable that Alice can do that acts only on A does not depend at all on the on what happened to system B, on the local evolution of system B. Okay, and this is essentially what is called the non-signaling principle between subsystems. So, and just by the way, so just to make this even more explicit, we can send the U's back out again. And we'll end up here with UA dagger of T, tensor identity on B, then this term of MA, HA. Let me bring this all down. Identity on B, UA of T, identity on B. Okay, Phi 0. So it's exactly the same. It's going to be the same result, the same average, as if the evolution had been such that nothing had happened on system B. Okay. And now we're going to see an example of this. And we're going to see only the beginning of the example. And this example is going to be the Stern-Gerlach experiment as promised. I don't trust my software enough to press pause to go get some water, in case you're wondering. So as we saw, the global heliospace is going to be the spin of the electron, and then the x coordinate, and then the y coordinate for now. Okay. There's also a z coordinate, but we don't have to write it all the time. We will not measure anything there. So that's the y. That's going to be kind of the x. And the idea is that this experiment has kind of three regions. Let's write them down. There's going to be a region A where it starts, and then there's going to be a special region B, and then a very long region C, and then there's going to be kind of a screen. This is just a screen. I'll write it here. So at this point, what we'll do is here measure x by letting, so there's going to be an electron flying around, and in this middle region we're going to have a magnetic field. This 0 in delta, which is going to couple some internal and external degrees of freedom of the electron. And we want to start with a very nice Gaussian wave, which will evolve. So it's going to start with some momentum just going up. And then, as we saw, it's going to spread out a bit. And then something will happen here in the magnetic field that it will couple. It will couple the momentum on x to the spin of the particle, such that we're going to have a superposition of a particle going left and right. It's going to spread out even more. And then in the end, we're going to measure just the x position, and it's going to be correlated with the spin of the particle. Okay. So first, let's just think about how we'd represent the total Hamiltonian of this thing. So we want to have some h global, a total h that's going to be some h0 plus some h of interaction, where h0 is just a free particle, so it's p squared over 2 mu, by which we mean nothing happening to the spin, plus sorry, times hello, times px squared times nothing happening to y plus the same py squared. Okay, good. And this h interaction, well, it's going to be something that will couple, which we will not see completely today, because this requires us to go into angular momentum, which we have not studied yet, so we'll leave it alone. But all we need to know is that it acts on systems S and X. And on Y, well, the only function that Y will do is to tell us where this Hamiltonian acts, and we want it to act only in this region here, okay? Which means that we put here a projector, let's call it projector delta on Y, which is up to Y from 0 to delta. Okay. So the way what the function of this is tell us that in this region over y there is this Hamiltonian acting on the other two, s and x. Now we don't have enough knowledge yet to compute right away the whole evolution of the whole thing, so what we'll do is think what happens if you had only region A first, and then in Tuesday's lecture we'll continue to analyze the experiment. Okay. So let's take an example of an initial wave function. An initial state, for example. So I want something on spin that's uncorrelated from the position initially. Right, so I have and so for the position I want to have a 2D Gaussian that is moving up, right? Is moving along y direction only, and I want this to be uncorrelated with the internal degree of freedom, because that's the whole point of the experiment, is to correlate the two. So we start with something that's uncorrelated. Okay. So then let's say that, so the whole wave function at time 0, x and y, this is going to be something on S, tensor something else on x and y, where this thing on S could be anything, and for now we just expand it in the 0, 1 basis, okay, with some coefficients. And the whole point of the experiment is to try to work out what these coefficients are. Yeah. And now for the position wave function, we just take a Gaussian, but in 2D, which is just a straightforward generalization. So we have the two integrals. Dy, okay, y. So this means that it's only moving in the y direction. And now here are the states. And we want this thing again to be the wave function of the script of a Gaussian, which I think would be something like this. X minus x. And here is the y minus y0 over 2 sigma squared. Okay, so now think that this, we could have tweaked the Gaussian more. We could have had different sigmas for x and y directions, but we want to keep things simple. Okay, so what are the averages now? Average x is x0, average y is y0, average momentum over x, so times 0, is R0, average momentum over y is h bar k, and we read this from here. And the variances are delta x squared sigma squared delta sigma squared delta px squared is h bar over sigma square. And the same here, because again, like I said, we kept things fairly symmetric when we defined this light blue wave function. Okay, which means now if we kind of draw the wave function from above, by which I mean, let me tell you in a bit, x, y, x0, y0. Oop. It's clearly a circle. Don't be difficult. Oh, that's not a circle. Clearly a circle, yes. And what's in the circle is just kind of the region that has high probability. Okay, so the wave function looks like this bell curve, both in the x direction and on the y direction. And this is like we're seeing from above, and what's in dark is just the points where this probability is above. It's above some number, right? So anyway, it looks like this, and the diameter of this circle is kind of sigma. And in the p basis, with py and px, and it's the same. Clearly a circle. Good. Except it's centered here. Where this would be h bar k, and on x there's nothing, right? And same idea, like we're just seeing the regions of high probability, because I cannot draw in 3D. This thing. And again, if we care about any observable also on the spin system, for example, we want to know z. Well, this is going to be the probability of getting 1 is alpha squared times 1, plus the probability of getting 2 minus 1, which is beta squared, times minus 1, right? It would be just this. So that's if we wanted to know that. Good. So that's our initial state. And now let's suppose that we will let it evolve, and there's only region A. Okay, so there's only a region where the only Hamiltonian is the free particle Hamiltonian. So after some time t, and we want to know what happens, so let's just write what the evolution Hamiltonian is. And like we saw, it's nothing happens on the first system, which is a spin. On x we had minus t h bar, and here's p squared on x mu times the same thing happening on y. Okay. And now again, if you want to know how each of these observables that we saw before evolves, we only need to care about, because it's completely non-interactive, we only need to care about the local evolution, right? So if you want to know how z evolves, that looks only at the spin, we don't need to worry about this. If you want to know how x and px evolve, we don't need to worry about those two terms. And if you want to look at how y evolves, we really only need to look at that kind of evolution. Right, so this is just direct application of what we saw before, which means on z nothing happens. We can just apply the formulas we had before. That's just the same as z at time 0. That's alpha squared. Minus beta squared on x well, we saw that there was no momentum over x, so we still have x0. So delta x squared times t is this thing we saw before in the beginning of the class for a Gaussian, so 4 squared t squared sigma tuk, and that's going to be the same for y squared times t, right? Whereas on the other hand, the average position, this did change because we had some momentum. Px at time t is still 0. The variance is still h squared over 4 sigma squared, which is the same as the variance over py squared times t. And finally py at times t still h. Okay. So if we draw this, again the same kind of phase diagrams. Sorry, px here and py there. So now we have a much wider variance, and it moved only in the y direction, so big circle up there, where that's why. Oh, okay, it's no longer shape. This is y0 plus hk t. Oh, I forgot here. Good. This is x0 still. And on P, we continue to have a small ball. Pain. It's perfectly round. It was perfectly round. Don't be difficult. There we go. Over h bar k. Okay, so this is what happened, which is very consistent, if you see, with my drawing here. Okay, now in the next class, we'll see what happens in regions B and C. And still with a toy example, but that will already allows us to compute some things. Good, so thank you for your attention. I know this went a little bit over time, but I thought it was important to have everything very clearly explained. And I'll keep the next lecture a bit shorter. Okay, thank you, and see you next time.